Hello and welcome to my SIGDIAL 2020 presentation. My name is Stefan Ultes and I am presenting our work on similarity scoring for dialogue behavior comparison. Evaluation of spoken dialogue systems often relies on absolute metrics like task success. And this is good and makes sense and is very important. However, in evaluation like that is only superficial. Consider those two system variants performances. They achieve very similar task success rate. Have you ever asked yourself if this success rate comes from similar system behavior, or maybe their systems do something completely different but still achieve the same success rate? We can only answer those questions if we look deeper into the behavior and compare those two models on a deeper level. And this is important if we want to deploy a specific model for a real application, or if we want to understand better what those models have actually learned. And questions we might want to ask are, when does the behavior of a learned dialogue decision model converge? Or which effect do modifications of the learning parameter or learning setup have on the resulting learned dialogue decision models? Do modified dialogue decision models result in exhibiting the same behavior? The goal of this work is to propose tools that help to answer such questions, and we call that problem similarity scoring. The remainder of this talk is structured as follows. I will continue presenting the scoring framework to score the similarity of dialogue behavior models based on a fixed set of contexts. Then I will present the similarity scores, which are used to quantify the similarity between two behavior models. And I will demonstrate the usefulness of this framework by presenting two application examples. The scoring framework is simple yet effective. It is based upon a set of predefined contexts, and each of those contexts is fed into the behavioral models we want to compare with each other, and the resulting system action is then collected and fed into the scoring function to compute the final similarity score. And here it is independent whether the behavior model comes from a modular spoken dialogue system taking symbolic input and generating symbolic output, or it represents an end-to-end neural dialogue generator. In fact, you can actually even compare behavior models coming from two different worlds. Obviously, the dialogue contexts play a major role. A dialogue context represents a sub-dialogue either by a sequence of system and user utterances, or on a symbolic level by a dialogue state. And those contexts are either collected from real interactions, which has huge advantage that you only end up with realistic contexts that might end up in actual interactions. However, they are very hard to control because you cannot just assign properties to those. On the other hand, you can generate contexts with the properties you want them to have. However, they might be unrealistic and not occur in actual interactions. While we have both types, collected and generated contexts, in the paper, in this talk, I will only focus on collected contexts. The similarity scores are on two levels, the semantic level and the textual level. On the semantic level, we have the total match, which compares both semantic representations of the system response, and only if they match on all aspects, this is a match. Then there's a dialogue act match, which is a match if the dialogue act is the same. And to have a more fine-grained idea of similarity, there's a concept error, which is similar to the word error from the speech recognition system, and it builds upon the Levenshtein distance of two semantic representations. But as this is asymmetric, we also propose the concept match as a symmetric way of doing something similar, where the ratio of common concepts of two semantic representations and the total number of unique concepts of both is used. If you have a system that doesn't have this semantic level, then you can rely on the textual level, where we propose the sentence level semantics represented by the universal sentence encoder. And there you can use the cosine or the angular similarity of the vector representations of both textual system responses. Then there's BLEU, which comes from machine translation, and I suppose all of us know it already. It's basically a score that uses word overlap counts. And finally, there's BERT score, which compares those two utterances by using the BERT representations of the tokens, and each token of one utterance is then matched with a token of the other utterance using the maximal cosine similarity. And based on those matches, the harmonic mean is computed. All those scores, the textual and the semantic level scores, are defined in much better detail with equations and everything in the paper. To demonstrate the usefulness of the similarity scores and the scoring framework, we've applied those to two application scenarios. First, to test for seed convergence, where we ask, do dialog decision models from different random seeds result in exhibiting the same behavior? And for policy comparison, where we ask, to which degree do dialog decision models from different reward models exhibit different behavior? The experimental setup we use is based on simulated dialogues in the ChemRestaurant domain using PyDial as a statistical dialog system toolkit. We use two different reward models, one based on task success and one based on interaction quality. And to validate the learned models, we look at the absolute measures, task success rate, average interaction quality, and average dialogue length. And for each reward model, we train 3 different policies from 3 different random seeds for a total of 40,000 training dialogues to make sure that each model has converged. And if we see those numbers, we see that those numbers reflect and are in line with what we know from related work. We have first used this setup to test for seed convergence using the task success-based reward model. Here we can see the total match rate, the dialog act match rate, and the USE cosine similarity over the course of the training steps, up to 40,000 training dialogues for each policy originating in a different random seed. Or rather, comparing the policies that originate from different random seeds. And as you can see, that policies 0 and 2 actually converges towards rather similar behavior, matching up to 90% in the end. But policy 1 goes a different way and does not converge to the same behavior. This analysis on the semantic level is confirmed by the analysis on the text level by the USE cosine similarity scoring, where we do see that the similarity is more similar with policy 1 and less similar between policies 2 and 0, which is a result of the wording that results out of the semantic representations, where you do have more overlap. On the dialog act match rate, we can see that all policies converge towards a rather similar behavior in terms of dialog acts, but still there's a difference between policy 1 and policies 0 and 2. Now, using the setup for policy comparison of policies trained with the reward models of task success and interaction quality, we see that the total match rate is not very high and that the policies do result in different learned behavior, both in terms of total match and also in terms of dialog act match, although this is much higher. But interesting fact is that when you compare the policy comparison results with the seed convergence results, which are the last 6 bars that which just appeared, you see that the differences when changing a random seed is similar in magnitude when changing a big thing like a reward model. Now we can give answers to the questions. The learned dialogue decision model converges in terms of behavior after 40,000 training dialogues. Almost, there are still small changes visible, which you can derive from the results in the paper. Now the results I've just shown here, we can see that the change in random seed results in differences in the learned behavior, as well as a change in the reward model. And those differences are even similar in magnitude. To conclude, I have presented the similarity scoring framework as an important step towards a more detailed analysis where each model is evaluated with a fixed set of dialogue contexts to compare resulting system actions. The framework allows for comparison of modular and end-to-end systems even with each other. We've presented 8 different semantic and textual similarity scores that cater different needs and showed its successful application on different application scenarios. For future work, we want to go more into the fine-grained analysis by looking at subsets of contexts that have certain properties to get more insights on that level. Also comparing 2 responses on the single context level to identify interesting situations. If you're interested in this work, please read the paper, and if you have questions or comments, write me an email or come later to the live QA session. Thank you very much.